Package theft has become a growing problem as online shopping continues to increase, leaving many deliveries unattended and vulnerable. This raises an important question. How can we better protect our packages? For our semester project, we designed and constructed a smart anti-theft parcel lockbox called SAFE, which stands for Secure, Automated, Fast Encasement. The members of our group are Brianna, Elliot, Michelle, Kelly, Elam, Elijah, and Natasha. As online shopping continues to grow, more deliveries are left unattended, making them easy targets for theft or damage. While tools like cameras can record these incidents, they don't stop them from happening. The goal of our project was to develop a system that not only monitors deliveries but physically protects them. Our smart parcel lockbox is designed to receive packages and secure them immediately after delivery, reducing the risk of theft or tampering. By combining automated mechanisms with sensor-based detection, our lockbox provides a more preventative solution that improves both security and convenience for users. Our system is built around a Raspberry Pi Pico microcontroller, which acts as the main controller and coordinates all sensor inputs and actuator outputs. The system uses 4 sensors: an infrared IR sensor to monitor the front door's position and manage the front door lock, a force-sensitive resistor to signal when the tray has reached its limit and stop the motor, an ultrasonic sensor to detect an approaching delivery person, and an accelerometer to sense movement or tampering. In addition, the system includes actuators, consisting of 2 servo motors and 1 DC motor, which control the motion of the tray and the locking mechanism, as well as a buzzer that activates when the box is tampered with. The working principle of our smart parcel lockbox is based on sensor detection and automated control. The system remains in an idle state while continuously monitoring for a delivery person using an ultrasonic sensor. When the delivery person approaches within a set distance, the system activates and unlocks and opens the front door while simultaneously supporting the plate mechanism. Once the delivery person leaves and the package is placed inside, the front door automatically closes. The infrared sensor detects when the door has fully closed, which causes the lock to engage while simultaneously allowing the plate mechanism to lower. After the process has been completed, the DC motor activates to raise the plate back to its idle position, while the force-sensitive resistor monitors the applied force and stops the motor if pressure is detected. An accelerometer continuously monitors for movement, triggering an alarm if tampering is detected.
We will now show a short video demonstrating the functionality of our hardware prototype. These 2 videos respectively showcase how the locking and the plate mechanism move.
For our coding, the project utilized parallel programming across 2 Raspberry Pi Picos, which were separated into 2 major task flows as follows. Note that these 2 Picos are listed with their sensors and actuators, which they will be controlling. The project started with the coding of Pico 2 and its anti-vandalism alarm program with the accelerometer and the buzzer. In this program, we use MPU, which is a module required for the accelerometer itself. We designate the buzzer's PWM pin and set it to 0 by default, and then check if the pitch or roll is more than 15, then sound the alarm. We then program the IR beam sensor, which is a simple binary output which we would utilize for locking after the door closes. Then the ultrasonic sensor, which would be used on Pico 1, which controlled the opening and closing of the door. This code eliminated invalid readings so that we could single out erratic readings during testing. Then we move on to the 2 servos. In the code, we designate the pins as PWM on GP15 and 16, set their frequency to 50 Hz for the SG90s, and then define a function to map the values of PWM to the servo's degrees of rotation, with the minimum and maximum being 0 and 180 degrees, or the value for 0 and 180 degrees respectively. We then convert a given input value for degrees and convert it into a duty value and then send it to the servo in lines 14 and 15. We then define another function to move the servos, which puts small delays into the movement of the servo to slow it down, move smooth, and also designates the target and starting angle for that. After that, we move on to the main loop of the door unlock. Using this program while the user persists, the door stays open but closes once the user leaves the sensor's range, which then triggers the IR beam to lock the door once the door is actually closed, which activates the plate dropping function. As for the plate dropping mechanism code, we decided to on a DC motor for simplicity, so we only had to worry about 2 pins, as shown here in 1 and 2. Our motor was driven by the L298, which allowed us to just need to have those 2 pins. We had also designated a force-sensitive resistor into this code on GP27 for the purpose of stopping the motor once the plate puts pressure on the resistor. Then we defined the main function of the plate mechanism code. We had assigned another helper function to Pico 2 to also check if Pico 1 had sent a message through UART, which is shown here. This part of the code utilizes the easy comms modules the module to facilitate communication between two picos, just from pico 1 to pico 2, which then activates the drop plate function, and then the picos are brought to their dormant state after the plate rises up. With this code, we were able to allow for leniency during testing with smooth movement of the door and avoid overloading one pico with all the data.
We hope our video has given you useful insight into the design and development of our smart anti-theft parcel lockbox, and how engineering can be used to improve everyday security and convenience. Thank you so much for watching!